Hi, this is Ahmed Salah from Physics for Life. A ball rolls down a ramp and into a horizontal surface. The first section of the horizontal surface is smooth. The second section of the horizontal surface is rough. Figure 1.1 shows a speed time graph for the ball when it moves. Actually, the first part of the graph, I can read it. It means the speed is increasing or the acceleration is constant because we have a straight line with a positive constant slope. And the second section, as you see here, it's a horizontal line. It means the speed becomes constant. I can see that the acceleration even it's zero because the slope is zero. And there is no, even we can add, there is no force acting on this stage. The last part of the graph shows that the speed decreased with a higher rate. It means the acceleration is increasing but in negative. It means the speed get decreased until it reached to zero at time equal 3. This is all information that I can see right now. State the time when the ball reaches the start of the rough section of the horizontal surface. I can see that in the graph. When the ball rolls over the ramp, it was accelerating due to the component of its weight towards the gravity or towards the center of the earth. Once when it reached to the horizontal surface, the smooth part, the speed becomes constant. And then when it gets inside the rough part of the horizontal surface, it decelerates because of the resistance back or the resistance of the surface, or we can say the friction of the surface, of the rough surface. So I can write that the time can be given here in this point, as you see here. Then I can extend a straight line down. Yeah, I can read it. It's exactly, looks like it's 2.2 seconds. So in 2.2 seconds or at 2.2 seconds, the speed decreased. It means we get inside the rough section. So I'm going to write 2.2 seconds. The other part of the question, explain how figure 1.1 shows that there is no resultant force on the ball when it rolls along the smooth section of the horizontal surface. I mean, this part, during this part of time, when it moves over the horizontal smooth surface, the speed was constant, the direction was constant, so the acceleration is zero. I mean, the slope is zero, so there is no acting force or there is no resultant force. So I could write that down here. The graph is a straight line. The graph is just a straight line. Horizontal line between, I just need to localize the time, 1.5 to 2.2 seconds. It means the slope is equal to zero, and that means the acceleration is zero, and that means the total force acting is zero, and this is what they ask you to prove. And we got some information from the graph. As you see here, we mentioned the slope of the graph, and also we mentioned the graph line. The second part, or the second question, the next page. I use figure 1.1 to determine the acceleration of the ball as it rolls down the ramp. As you see from the graph, the acceleration should equal to the slope, right? In figure 1.1, determine the acceleration of the ball as it rolls down the ramp. This is the first part of the graph, which was a straight line with a positive slope. So I could write here, the acceleration, it's equal to the slope of the graph, which is change in y divided by change in x. Let's check it out. The first part of the graph, I can take the reading here for the maximum triangle, the maximum triangle here that we have. This is 12. It seems like 12 point. So here we have 13. That was 13. And this is 12.8. So I'm going to write here 12.8. And when you go down with that section here, the time is 1.5 seconds. So I could write change in y divided by change in x. So I could write that down here, equal to change in y, which is 12.8 minus 0, divided by change in x, which is 1.5 minus 0. If you use your calculator, that gives you 8.5 meter per second square. So I'm going to write here 8.5 meter second minus 2, or per second square. That was the acceleration. The last part in the question, the pulse starts from rest at the top of the ramp, show that the length of the ramp is 9.6 meter. That's great. We can use the equations of motion because we have many things. I can write that down here. Remember, writing below the marks here, it couldn't be seen by the examiner when he corrected your paper. So please stick with the area provided for the answer. But I just need to tell you that we have the acceleration and we have the time. We can get the time from the graph. And also we have the initial speed, which is 0. It's just mentioned. So we have all information that we allow us to use this equations of motions. So I could say here, since the displacement equal to ut plus half at square. Ut is 0 because the initial speed is 0. So half the acceleration we just calculated, it's 8.5. And we still have the time. The time from the graph is from the beginning to the end during this period of time. So from 0 to 1.5, it's 1.5 seconds. So I'm going to write here 1.5 seconds square. So if you use your calculator to do this calculation, it's going to equal 9.6 meter exactly. And this is what they said here. That was the first question. The second question, I think this is about Hooke's law. Figure 2.1 shows a spring balance used to measure the weight of a baby. The spring inside the balance extends when a mass is suspended from it. The deal shows the extension of spring as value of mass in kilograms. Let's see. State Hooke's law. You know Hooke's law, as a statement, I could write F equal to K Hooke's constant times X or times the extension. But I prefer to write it in words. It will be much better, like the force equal to Hooke's constant times the extension. Anyway, whatever the way you write it, it could be correct. State the relationship between the mass of the baby and the force exerted on the spring due to the weight of the baby. The force exerted on the spring, it's the weight of the baby. So I can write here mass and the weight both are directly proportional because the gravity acceleration is constant. So when it comes to the second law of Newton, I could say F is directly proportional with the mass. This is more than enough. The reading on the spring balance is 8 kilograms. Determine the force exerted on the spring due to the baby. So I'm going to write here the force equal to mass times gravity acceleration. The value of the gravity acceleration has been given on the cover page of the exam, which is 10. So the mass here is 8 kilograms times 10, gonna equal 80. So it could be 80 Newton. That is the force B. the limit of proportionality of the spring is at a force of 175 Newton. Sketch the extension load graph for the spring. The sketch must continue beyond the force of 175. You know it's supposed to be straight line starting from point 0 because it's just extension. So once when it comes to the extension, it means it's a straight line. And once when we pass the limit of proportionality, as they said, the extension will increase by an expected length, which is more than usual. So it could be a little curvy. So I'll make a curve up to the up direction. It means the extension, by increasing the force beyond 175 Newton, it becomes more than as it's expected before. So we got two marks for the graph here. The first part for the straight line and the second mark for the curvy line. The baby is carried from the ground floor to the bedroom. The vertical height of the bedroom above the ground floor is 3.5 meters. Calculate the change in gravitational potential energy of the baby when it's carried from the ground floor to the bedroom. The change in gravitational potential energy equal mg delta h. So once this is the law, we have mg, it's 80 Newton, times, so let me explain that. M here is 8 and g is 10. So mg means 80 times the change in height from the ground floor to the bedroom. It's 3.5 meters. They mention it here in the question, so it could be 3.5 meter, equal to, it's 280, and the measuring unit, this is just an energy, so it could be in joules. So 280 joules. That was the second question. Up to this moment, we have no difficult questions in this paper. In question 3, said figure 3.1 and figure 3.2 shows how a barrel of water changes on a warm, windy day. This is a barrel of water, the figure to your left hand, over a solid root surface. Then they said after 3 hours later, the barrel of water becomes a little bit smaller. So describe the process by which the volume of water in the barrel decreases. So the process here is evaporation. So it's just evaporation. I can write it clearly here. It's evaporation, or the water get evaporate. The water get evaporate. Or it is a process of evaporation. So we can say that the most energetic molecules on the surface escape and change into gas, so the total volume becomes less. Right? This is the idea of evaporation, how it could happen. So I'm going to say here the most energetic molecules on the surface escape and change into gas, so the volume decreased. Okay, fine. This is more than enough for the 2 marks. State and explain one change in the weather that would cause the volume of the water in the barrel to decrease, but more slowly. So it could decrease anyway, but the decreasing will be happen in a slower rate. I could say here, if it was a cold weather, like the statement here, what would happen to the weather, as they said, state and explain one change in the weather. So I could say here cold weather, or the temperature is less. Right here, cold weather or colder weather. The explanation here means it could reduce the kinetic energy of the molecules at the surface, then it means reduce the rate of evaporation. That was B. Then C, the last part of the question, explain in terms of molecules how sweating helps to cool your body on a hot day. This question repeated many times in the past a few years. We could write that during a hot day, the molecules of water, the sweat, change into gas, evaporate, taking the most energetic molecules away. So the remaining molecules have less energy and also have less temperature. Let me write that down. During a hot day, the molecules of water actually, here the sweat change into gas, and this is what we call evaporation. And it causes taking the most energetic molecules away. Taking the most energetic molecules away. You can add here the remaining molecules have less energy and less temperature. Have less energy and less temperature. That's fine. That was enough for 3 marks. In question 4, a sample of sand has a volume of 0.05 meter cube. The density of the sand is 1,900 kilogram per meter cube. The specific heat capacity of the sand is 1,500 joule per kilogram degrees Celsius or Kelvin, because this is just a change in temperature. Calculate the mass of the sample of sand. Here we have a volume and we have the density, and there is a relation between them, and I could write any density equal mass over volume. It means the mass, or since the mass equal to density times volume, the density has been given, which is 1900, it's over here, times the volume, which is 0.050. This is the volume of the sand. If you use a calculator, the answer is 95. I could write 95, and the measuring unit is kilogram, because meter cube will be cancelled, meter cube in both these measuring units. So the measuring unit is kilograms. I'm going to write 95 kilograms. That was the mass. Calculate the thermal capacity of the sample of the sand. We cannot say thermal capacity for sand because this is not 1 kilogram, or it's not the unit of mass. We ask about the thermal capacity for this sample. So just a reminder, I want to remind you with this laws that we studied, like C equal Q divided by M delta T. C here is the specific heat capacity. Q capital, it's the amount of heat energy. M, it's the mass. Delta T, it's the change in temperature. And also remember that law, Q small, this is the thermal capacity or heat capacity, and this is what they ask about. It's equal to Q divided by delta T. So if you take a closer look for these two laws, we can write it like C equal Q divided by T. It could be Q small, still divided by mass. That means thermal capacity, which is Q, equals C dot M. C is the specific heat capacity, which has been given here. It's 1500. times the mass, which is 95. If you use your calculator, you will get this answer like 1.43 times 10 power 5. So I'm going to write it here, 1.43 times 10 power 5. Do not mess the measuring unit. Heat capacity could be measured by joule per degree Celsius. It's the same like specific heat capacity, but there is no kilograms here. There is no mass. It could be joule per degree Celsius or Kelvin, because this is just a change in temperature. Then the other part here, the initial temperature of the sample of sand is 7 degrees Celsius. The sample of sand is heated using an electrical heater. The power of the heating element is just 50 watt. Calculate the time taken to increase the temperature of the sand from 7 to 19 degrees Celsius. Let's go through this. Just remember, the law for the specific heat capacity, we just wrote it over there, which is C equal to heat energy equal power times time when it comes to electrical method. So the power of the heating element times the time of switching it on divided by the mass times delta T, the change in temperature. I'm going to give you the specific heat capacity. I have everything, I just need the time, so I can rearrange the equation to find the time. So depending on that, the time could be C m delta T divided by the power. It means, the time is specific heat capacity was 1500 times the mass, we just calculated, it's 95, times the change in temperature, it becomes 19 after it was 7. When you use the calculator, make sure that you put the brackets to keep the priority for what's inside the bracket. Divided by the power. The power has been given 50 watt. So if you do that in your calculator, so the answer will be 34,200 seconds. So I'm going to write that 34,200 seconds. And also you can write it in minutes by dividing by 60. So I'm going to give you 570 minutes. And also you can divide it by 60 again to find it in hours. It will be around 9.5 hours. So it could be 9.5 hours if you wish, but any one of them will be enough. Could be in seconds or minutes or hours. It's just the time. The next part here, in the same question, they said, in some countries, the soil is too cold for plants to grow well. In these countries, plants are grown in a plastic pots and kept inside. So the pots containing soil are placed on sand. The sand is heated using an electrical heater as shown in figure 4.1. As you see here, we have a heating element inside the sand. Then over the sand, we have the plastic part, and inside it, we have the planet and the soil. The question is, describe in terms of molecules how thermal energy is transferred from heated sand through the base of the plastic pot. All are solids, so I'm expecting the word here, when I correct this question, I'm expecting the word conduction. So I could write, by heating the sand, its kinetic energy will increase. So the increasing in kinetic energy will transfer to the base of the plastic pot. And the kinetic energy of the molecules of the plastic pot could increase, increasing the temperature. And the heat energy will transfer entirely by conduction. So I could write it in points like number 1, by heating the sand, its kinetic energy increases. The second part is the heat energy could transfer to the base, the base of the pot. So the heat energy could transfer from the sand to the plastic plant pot. And increase its kinetic energy, and that happens by conduction, because all are solids, as you see. I think we still have, yes. The last part in the question, they said, the heating elements in figure 4.1 remain switched on. The temperature of the sand remains constant at a value above room temperature. So the heating element still working, but the temperature is still constant at a value above the room temperature. Explain why the temperature of the sand remains constant. They mean while the heating element is working, why the temperature is not increasing, it's still constant. So I could say here, this is what we call thermal balance. The amount of heat energy in equal to the amount of heat energy out to the surrounding. So I can write here, due to thermal balance, or due to what we called it, thermal balance, so I could write the heat energy gained, the heat energy gained by the heater equal to the heat energy lost to the surrounding. This is the idea of that question, nothing more. That was question number 4. In question 5, we reach to waves. In question 5, a body looks at the image of a clock in a plane mirror. Figure 5.1 shows the mirror, the clock, and the position of one of the boy's eyes. Okay, so we can see that in the figure. We have the boy's eye symbol and the mirror, then the clock. On figure 5.1, draw a ray of light from the clock reflects to the boy's eyes. To be honest, to draw this, it will be a little difficult and take some time. If you use the protractor to measure the angle of incident and make it exactly equal to the angle of reflection, it takes time. So the other idea that we explain it during the course, you need to draw the image in its right place. It could be exactly in the same distance. I just measure it. So the clock image will be over the mirror here. Okay. And the line connecting between the clock and the mirror and the clock image should be straight line, and this line make a right angle with the mirror. And in this case, you need to just extend the ray to the eye. No, this is not the exact ray. This is part of the ray. So this should be dotted. I'll make it dotted. Okay. So we have extension of the ray beyond the mirror, and we have ray in front of the mirror. Then what you still need to do is just connect the ray from the clock to the point of incident over the mirror. So here we have two rays. This is the incident ray, and this is the reflected ray, and we have the extension ray on the back. I did not measure any angle, but I'm sure if you put the normal and measure the angle of incident, it could equal to the angle of reflection. So right now, we did the first two questions. On figure 5.1, draw array, we did. to the eye and mark with an X the position of the image. So I just need to write here X, and this is the position of the image. State whether the image formed by the mirror is virtual or real. I'm going to write it virtual. The reason behind that, because as you see here, it's formed by extension of rays, not rays. It is formed by extension of rays, not real rays. The next part of the question, figure 5.2 shows the image of the clock seen by the boy. This is the image in the mirror. So the boy now looks directly to the clock. On figure 5.3, draw what the boy sees. You know, from the property of that image, it should be reversed. So I will draw the longer wise as it is, and the smaller one, it could be to the opposite direction. Instead of right, it could be to the left. This is one of the properties for the image formed on a plane mirror. That was easy. The last part in the question, they said, the clock is illustrated by a source of monochromatic green light. State the meaning of monochromatic. You know, we have monochromatic, dichromatic, tetrachromatic. The idea of, or multichromatic, the idea of this, the word mono means one, so I could say here, it is a ray with a single frequency and single color. It is a ray with single frequency and single color. The green light has a wavelength of 5.6 times 10 power negative 7 meter. Calculate the frequency of the green light. You know, and a frequency equal velocity divided by the wavelength. And I got 1 mark for the low. The velocity, it's supposed to be 3.0 times 10 power 8. Then divided by the wavelength. The wavelength is 5.6 times 10 power negative 7. If you do that in your calculator, you will get this answer. For me, it's 5.36 times 10 power 14. So I'm going to write here, maybe it could be 5.4 times 10 power 14. Do not miss the measuring unit, which is hertz. Fine. The next part here in question 6, electromagnetism. Figure 6.1 shows 2-pound magnet. On figure 6.1, sketch the pattern and the direction of the magnetic field lines between the palm magnet. Well, let's do that. You know, it could be a straight line coming from N towards S. Try to make it straight as possible. And the distance between two successive lines is supposed to be constant, so you can do that. And the direction. So the distance, it has a mark, and the direction from N to S, it has the other mark. Figure 6.2 shows the same bar magnet with a coil of wire between them. They said, name the part labeled A in figure 6.2. This part is 2 slip rings. So we have 2 slip rings or 2 split commutators. They are not splitting here. This is just 2 complete rings. So I'm going to write it's 2 slip rings. Fine. The coil of wire is rotating in the direction shown in figure 6.2. Let's see the direction here. If my eye in this position, so I'm going to see the rotation as the direction of clockwise, right? So in figure 6.2, draw an arrow to show the direction of the current in the coil. Explain your answer. So I'm going to use the right hand rule because this is a generator, and in generator we usually use the right hand rule to detect the three directions for the magnetic field lines and the direction of the current and the direction of the force acting. So I'm gonna set my hand, my right hand, from N to S. My finger will sign from N to S, and this shorter finger will direct it as a force which is up. I'm talking about this arm, guys, here. This arm in red, let me make it in red. So when it comes to that arm, the arm is moving up. So my smaller finger will be directed up, and the other finger from N to S, and the longer finger will tells you the direction of the current. So the direction of the current will be into the beige. This is I. If you do the same in the other arm here, so the force is down. So I'm gonna flip my hands from N to S. My finger from N to S stays the same. My smaller finger could be directed down, and the current will be outside the beige. So the current is outside the beige here, right? Anyway, they just ask you to show the direction of the current, so you need to draw one arrow to show the direction. So I'm gonna choose this part. So the direction of the current is into the beige in this arm. One arrow is enough, right? And they said, explain your answer. There is no explanation here except you could mention that you are using the right hand rule because this is a generator. So I could say here, by using the right hand rule, the direction of the current is as shown. Okay, fine. That was this question. Explain how rotating the coil in figure 6.2 continuously causes the galvanometer needle to show an alternating current. So the direction of the current will be alternating from right, left, left, right, and so on. So we could mention, we have 4 marks here, so we need to write some different information, like by rotating the coil, it could cut the magnetic field lines, and there is a current produced. After 180 degrees, for example, of rotation, the direction of the coil, when it cuts the magnetic field lines, will reverse. So the direction of the current will reverse again, and so on. So we will get a new direction for the current every 180 degrees. This is what I could write here. So number 1, by rotating the coil, it could cut the magnetic field lines, producing a current in a specific direction. This is the first part. The second part is number 2. After 180 degrees of rotation, the direction of the coil will reverse. So instead of moving up, I could move down and so on. So it means the direction of the current will change, and so on. And so on here means, this process could repeating every 180 degrees. It means, the current will reverse its direction every 180 degrees. And this is what we know alternating current. Question, that was the end of question 6. In question 7, figure 7.1 shows a circuit including a 12-volt battery and 2 identical lamps. The figure is so clear. The 12-volt battery consists of cells connected in series. Each cell in the battery has an EMF or electromotive force of 1.5 volts. Determine how many cells are in the battery. It's so clear, like the battery is 12 and each cell has like 1.5 V. So 12 divided by 1.5 gonna give you 8. So I could write here 8 cells inside the battery to give you the total EMF 12 volt. When the switch is closed, the ammeter reading 2.4 ampere, this is the total current, and they ask you find the total resistance. I said that since the resistance equal V divided by I, the potential difference is 12 as a total potential difference, or total EMF, divided by the total current produced, it's 2.4. So the right answer here will be 5 ohms. So I'm going to write 5 ohms here. It's better to write 5.0 ohm. Each lamp has a resistance of 3 ohm. Calculate the resistance of Q. In this part, each lamp, as you see here, 3 ohms, and they are parallel. So the total resistance for the battery could be 3 times 3 divided by 3 plus 3. So it gives you 1.5, right? If the total resistance is 5 and the parallel group is 1.5, so Q, it could be 5 minus 1.5. Let's see that in steps. Step number 1, since the resistance of the parallel group equal to 3 times 3 divided by 3 plus 3 gives you 1.5 ohms. It means the resistance of Q itself equal to the total resistance, which is 5, we just calculated, minus the resistance of the parallel group, which is 1.5. So the results here will be 3.5 ohms. So here we have 3.5 ohms. Fine. That was easy. And the next part of the question, or question C, on figure 7.1, draw a symbol for a voltmeter that measures the potential difference across the 2 lamps. Let's see. Across the 2 parallel lamps, I think. Difference across the 2 lamps. Okay, so the 2 lamps here connected parallel, so I need just to connect the voltmeter in this area. You can put it down or up, it doesn't make a big difference. So this is where the voltmeter should be placed. We did that for 1 mark. Calculate the power supplied to 1 lamp. The power could be calculated by VI, or V squared divided by R, or I squared R. But the idea is, it depends on the given. I can feel here, the easiest part to find the power for 1 lamp, I could use this law, since the power equal to V squared divided by R, and also the power could be calculated by I square R. This is also one of the laws, and I think this is easier, equal to. If the total current is 2.4 in the circuit, it means, and the 2 electric bulbs are already identical, so the current will be split between them 50% for each, right? So the current passing through 1 lamp, it could be half of the total current, which is 2.4 divided by 2. The total current is 2.4. So I'm going to write here I is 2.4 divided by 2 because they are identical. This is square. This is the current in each lamp. Could be square. Times the resistance of one of the lamps. And they said, the resistance is 3. They said here, the resistance of each lamp is 3. And this is what was written here in this part. So I'm going to write times 3. If you use your calculator, you will get like 4.32. The measuring unit is what? This is the power. So we could use that to find the power, I square R, or you can use V squared divided by R, but in this case, you need to calculate the potential difference across the resistance. And even if you know that you can find the potential difference if you used to go this way, I could write that power equal V square. V square here It could be calculated depending on IR. So the current passing on that could be 2.4 times the current, the resistance is 1.5. Then this is square divided by the resistance. The resistance is just one of these resistance, which is 3. So if you do this calculation, it could be the same power that we just calculate here, which is 4.32 watt. So just write any one of them, it could be correct. That was C. Double I and I. And that was also the end of the question. Question 8. A radio is connected to a main supply using a step-down transformer. Draw a label diagram for the structure of the structure of a basic step-down transformer. Remember, step-down here, it means the number of turns in the secondary coil should be less because it's step-down. So I'm going to write that down here, and the transformer should be something like that. And here I'm going to put another rectangle to give you a feeling of 3 dimensions. Then the wire to make the coil. We go over the wire now. And when I draw, I'll try to make number of turns in the primary coil as much as I can. And make it clear, and the number of turns in the secondary coil should be less. Yeah, it's so clear right now. In the primary coil, the number of turns is more. So I'm going to write that down here. This is the primary coil. And that one is the secondary coil. And here, this is the input. And that is the output. And here we have iron core. Fine. That's it. It's step-down transformer because in the secondary coil the number of turns is less, and this is what we just draw. They said here explain the operation of a basic transformer. The operation is we have 3 steps here for 3 marks. Told you about them during the course. So the AC current, number 1, the AC current in the primary coil will produce a magnetic field. This magnetic field will transfer to the secondary coil through the iron core. Then the magnetic field could be cut, the variable magnetic field could cut by the second coil to produce the alternating current in the other side with different potential difference. This is simply the 3 steps that we got 3 marks for them. So number 1 here, the alternating current or the AC induced a magnetic field, induced a magnetic field in the primary coil. Number 2, the magnetic field, or make it variable magnetic field, the variable magnetic field will transfer to the secondary coil through the iron core. Then the last part here, the variable magnetic field get cut by the secondary coil and produce the AC or alternating current. And for sure it could be different with different potential difference. This is enough for the 3 marks. The voltage of the main supply is 230 volt. The output voltage of the transformer is 6 volts. calculate the value of the turns ratio NS divided by NB, give your answer to two significant figures. That's easy because they said NS divided by NP. We have this law since you know NS divided by NP should equal VS divided by VP. We know this law. And that means VS, in the secondary is 6 divided by V in the primary, which is the input, is 230. By putting in the simplest form, it could be 3 divided by 115. In the calculator, it gives me like 1 over 38.3, right? And they ask you to put or to write it in two significant figures only. So by doing that in the calculator, it could give you 26.1 times 10 power negative 3. So I'm going to write it 26 times 10 power negative 3 to make it too significant. Or also you can keep it like 0.026. Both are correct because both are in two significant figures as they ask you. Right? That was the end of the question. That was easy about the transformer. Then we have something related to electronics. Figure 9.1 shows a digital circuit. It's so clear for me. This is and not. And not. Two logic gates in front of me. Explain what's meant by digital. You know the idea of digital here. It's just signal must be one of two discrete levels. Like it could be on, off. 1 out of 2. On or off. 1 or 0. This is the idea of what's meant by digital circuit. Right here, it's a signal. Or the signal, we can write the signal must be one of two discrete level. One of two discrete levels. As I told you, it could be on or off, one out of these, or 1 or 2, 1 or 0, one out of these, high or low. This is the idea. So this is what's meant by digital. So table 9.1 is a truth table for digital circuit shown in figure 9.1. It's clear. So I can write here, complete the columns C and D in the table. So you know A, B, if it was both 0 inputs, the product in AND, it's supposed to be 0. And when it passed through NOT, it could be 1. Then 0, 1 in AND, the product could be 0. And D here, it could be 1. Again, 1, 0, it's the same, still 0. And here we have 1. 1, 1, so the output in C, it could be 1. When it passed through NOT, it becomes 0. Right? The last part of the question, they said state the signal logic gates that would produce the same output D from inputs A and B. Single logic gates here means like it's one logic gate could do the work. This one logic gate called both together and not, it's called NAND. So you're going to write NAND. So this is the signal. Sorry, this is the single logic gate that could do the same function. Okay, fine. I think this is the last question about, yes, it is the last question about radioactivity. So the isotope americium 241 is represented by AM95 241. This isotope decays by an alpha emission to the isotope of neptunium NP. Complete the nuclide equation for this decay. Fine. You know, the easiest part for me, it's alpha. Alpha, it could be 2,4, helium without nucleus. Helium without electrons, so it could be 2,4. Neptunium here, because of that 2 closed with alpha, so 95 could be changed to 93, and 241, when I remove 4, it could be 237. This is what we have here. And in the next part, they said figure 10.1 shows a symbol diagram of smoke detector. The smoke detector contains a small sample of mercium 241. This isotope ionizes the air between the metal plates and the detector. Fine. So describe how the mercium 241 ionizes air. It's a good idea, like here, by emitting alpha. Alpha is positive, so these alpha positive will take the electrons out of the air molecules, so the air molecules becomes positively charged and ionized. So we can write that down here. By emitting alpha, americium 241 emitting alpha, so by emitting alpha, which has high ionizing effect, and also, it's positively charged. Alpha, which is positive, take the electrons out of air molecules, takes the electrons out of air molecules. So the air gets ionized. This is more than enough, because by emitting alpha, and alpha have a high ionizing effect and it's positively charged, so alpha takes the electrons out of air molecules, so the air molecules becomes or get ionized. This is the description. The last part in this question, they said suggest and explain 2 reasons why smoke detectors use an isotope that emits alpha particles rather than isotope that emits gamma radiation. Alpha, it has a very, very short range and also can be stopped inside the glass plate here, or the glass container here, or the metal plates. It cannot go outside the metal plates because it could be stopped, right? But gamma, it couldn't be stopped easily. And we can say also, and could be detect easy also. Alpha could be detected by the detector easier than gamma, right? So let me write that down here. Number 1, for example, we can say because alpha has a very small range, so it is safe. Alpha has a very small range, which is fine. Also, we can add 1 point here. Could be detect easy. Alpha can be detect easy. And also we could say, very small penetration. Very small penetration for alpha, so it couldn't go outside the experiment area. That's it. Can't go outside the area of the detector. So this is why we choose alpha rather than gamma. Thank you and good luck.